In this tutorial, I want to explain to you about the concept of fork join. Fork join is a special mechanism of using threads and concurrency in Java. There is a special API meant for a specific use case. So I'm going to explain to you what that use case is, where you would want to use fork join, and how to use it. So fork join is kind of, it's a set of problems which have a certain characteristic. A very common term that is used for this kind of solution and this set of problems is something you might have heard of called MapReduce. What MapReduce does, and it's kind of a similar pattern that fork join does as well, is take a large problem set. So let's say you have, you want to process a huge list of numbers, for example. Okay, there is a large problem set, and there are a bunch of different ways in which you can process this large problem set. One, you can do it in an iterative way. You could say, I'm going to solve this one by one. Okay, process one element by one element. But as you can imagine, that is going to be slow, and that is not leveraging the concurrency aspect. That's not leveraging multiple cores. So if you try to tackle processing a large set of numbers one by one, it's basically just one core working on it. So you do something like divide and conquer, right? You basically divide the problem set into several parts and then have like each processor work on those parts. So you might say, well, how many parts do I divide this problem set by? Okay, let's say you're asked to process like 1 billion numbers. Well, you can say, okay, I'm going to see how many processors I have. Let's say there are 4 processors. I'm going to basically split that 1 billion numbers that I need to process by 4. Well, you can do that, but what if the time it takes to process something isn't evenly distributed? Okay, let's say some numbers in that large data set will be processed very quickly, and some numbers will take a lot of time. So just dividing that blindly by how many processors you have is not going to split the work evenly. Okay, so what MapReduce does and what fork join does as well is basically break down the problem into smaller pieces, do it recursively. Okay, so there's going to be a first breakdown, which takes that 1 billion numbers in this case and breaks it down into 2 parts. And then each one of those is broken down further into 2 parts each, and then so on. So it's kind of like applying this recursively and breaking it down so that the smaller pieces can be solved, and then it all rolls up to a final result at the end. Okay, so that's what fork join is meant to do. Okay, I'm not saying here that fork join is exactly the same as MapReduce, but MapReduce is a good example. Like, we are familiar with MapReduce, it's kind of like a good starting point to learn about fork join. Okay, fork join is a special technique for handling work which can be broken into smaller pieces recursively, and having these smaller pieces which we acquire by recursively breaking down the problem, having them run in a concurrent manner. Okay, so here is the example, processing all the elements in a list. So here is a pseudocode for how you would process it if you were doing it recursively. Okay, so first thing, let's ignore this if condition over here. Okay, so basically you split the work into 2 pieces and then invoke the 2 pieces, kind of like do the processing for the 2 pieces and wait for the results. Okay, this is basically the recursive splitting of work. However, as with any recursive algorithm, there has to be an end condition, right? If you keep splitting the work, at some point the work actually has to be done, right? So what you do is you have this if condition to say, okay, this method is going to get called for the first step, or for the lowest step, it's being called recursively. So at some point of time, you can say, okay, my work is small enough. It's been split enough times, and the portion of work that I have doesn't make sense for me to split anymore. In that case, you do the work directly. Okay, if that portion of work that you're receiving is not small enough, you do the split and then kind of recursively call the same method for each of those 2 split pieces. Okay, this is in a sense recursively breaking down a problem into smaller subproblems, and you see this happening in a lot of recursive algorithms. The thing that's different with this fork join approach is that you are leveraging concurrency to solve these recursively. So it's not just one thread which is recursively doing this. You're breaking it down into smaller recursive chunks and then having those chunks be distributed across whatever multi-core processor you have, so that you can solve for those multiple recursive chunks in a concurrent manner. Okay, so for this, Java APIs have an answer, and that is something called a fork join pool. Okay, with the fork join pool, you can take this problem, you can take a single task, break it down into smaller subtasks, and have each of these tasks distributed across a thread pool so that you're not basically taking up just one thread. Right? So here is the problem, here is the solution for our problem, right? So let's say you want to process a large array. You take that array and then break it into two parts, and then you give one part to this guy, one part to this other guy, and then this is going to split into another thing and split into another thing. So what you're doing here is you're recursively breaking this down. You might wonder, well, what's the difference between doing this and just splitting the work to how many of our processors you have? Well, the advantage is, since they're smaller chunks, it really doesn't matter which core does it. You have the ability, now let's say you break it down recursively and you have like, 50 such tasks at the lower level. You can take these 50 tasks and distribute them to your available processors instead of having larger chunks depending on your number of processors itself, right? So there's a difference between taking this large task and splitting it into 4, which is your number of processors, versus taking 50 tasks and splitting it into 4. You have much more granularity, and if one task finishes sooner, you can assign another small task to it, right? The higher level of granularity allows you to distribute these tasks fairly across your limited set of processors. Okay, so that's the advantage of this. But now there are a few problems with this approach. If you were to do this, and if you were to leverage the current APIs that we've seen a thread pool, right? So let's say you were to recursively break this, have each task take up a thread in the thread pool. Well, it's not going to be ideal because a bunch of problems there. First, you're going to have too many thread instances. Okay, there's a lot of threads. So existing mechanisms will be too resource intensive. Okay, just take a fixed thread pool or a cache thread pool. I think cache thread pool is going to be the worst thing you can pick for this because it's going to just spawn new threads as and when your smaller chunks come in. So what you need is something lightweight because you have much smaller set of tasks. So you want the infrastructure around creating a task and allocating it to be as lightweight as possible because you're going to be doing it a lot. Okay, you have a large problem set. You're going to be recursively breaking it down. You're going to have a lot of small problems. So you need some kind of infrastructure to be able to solve these smaller problems quickly and efficiently rather than use the thread mechanisms, which just come with a bit of a cost. All right. So the Java APIs have an answer for this. And the answer is something called the fork join pool. Okay, so fork join pool is a special implementation of the executor service that we've been seeing all along, that we know and love by this point. It's a special implementation of this executor service specifically for this use case of recursively breaking a problem down into like a gazillion smaller problems. Okay, so this is the API. And in order to use this API, you need to create something called a fork join task. A fork join task is again a special type of task which is designed to run in a fork join pool. Okay, fork join pool is a custom implementation of the executor service designed to handle this use case, and a fork join task is a special type of task that you give to the fork join pool and say, hey, fork join pool, execute this. Right? So we need to understand how to use this API, and I'm going to explain that to you. The first thing you need to do is to create a task, create the special task called the fork join task. Okay, you will be writing your own custom implementation of the fork join task type, and you're going to write the code for breaking down a problem and kind of grouping them all and then accumulating the data from all of those smaller problems. Okay, and then what you do is you create an instance of the fork join pool, or let me be more technically accurate. You get an instance of the fork join pool. You don't necessarily create it always, and I'll explain what that is in a little bit. You get an instance of the fork join pool, and then you submit an instance of your implementation that you've written, the class that you've coded over here, to the fork join pool, and then the fork join pool is going to take care of it. Okay, so there are two types of problems that you can solve with this thing. Okay, so the first thing is when you have, let's say you want to process each element of an array, right? You want to say, let's say you want to add one to every element of the array, right? Very simplistic example. You're definitely not going to need a fork join pool for this problem. But let's say what you want to do is add one number to every element of the array. But what you can do is you can break that down into these smaller tasks, and each task is going to just add one to whatever portion of the array it finds. Okay, at some point of time, you're going to say, hey, this array is small enough. Let's say you stop at an array size of 1, and then you say, okay, now this is small enough, I'm going to add 1 to it. Or maybe a larger chunk of the array, and you're going to say, okay, this is small enough, I'm going to add 1 to all of this sub array that I have. Okay, so this is one way kind of a breakdown. The other kind of problem is you want to sum up all the elements in an array. Okay, in that case, you can still approach it recursively, but now what you need to do is you need to report the data back. Okay, so let's say you have a 50 element array and you want to add all the elements of the array. You can say, okay, I'm going to break it down into adding, this task is going to be adding all the elements of a 25 element array, and this is adding all the elements of a 25 element array, right? And this one's going to break it down into, I don't know, like 15 or whatever, right? So you're chunking down the problem into smaller problems, but then what you need to do at the end is kind of like accumulate them all back to the root. Okay, so let's say this one says the number of elements added together for this particular chunk is, let's say, 20, and this one says 30. Now this task, it is split into two, but then what it needs to do is add this result and this result together and report it back. And then this task is going to be adding this result and then summing it up as you go up. Okay, so there are two types of problems here. One is, it's one way, all you're doing is just processing and then you're done. There is nothing to accumulate back. Okay, the second is when you have each individual processing, but then the individual process itself doesn't matter. What you need is to sum it all up at the top. Okay, so there are two types of problems here, and those are the two mechanisms that you need to use, and you can do both of them with these set of steps. Okay, you create an implementation of the fork join task and then get the instance of the fork join pool and then submit an instance of your custom implementation of fork join task to the fork join pool and say, hey, go ahead and run it. Okay, so what does the fork join pool look like? So here is a simplistic diagram of what the fork join pool looks like. Okay, we've seen how the fixed thread pool and the cached thread pool, all those things look like. Okay, so let's assume these are individual threads. They were vertical, but now I've written it as horizontal for a specific reason. Okay, these are individual threads, and here is your blocking queue where all your tasks are coming in. Okay, you submit a callable to an executor service. What does it do? If there is an available thread, it uses it. If not, it waits in the queue. Okay, so the fork join pool has something similar like this, but what it also has is these individual queues for tasks. Okay, the problem is like each individual task can create subtasks and they can create subtasks and so on. So you have a lot of tasks. So if you were to create one main queue for all the tasks, then this is going to be pretty big. So what the fork join pool does is it says, okay, now each of these tasks can create subtasks. So what I'm going to do is I'm going to have this, let's say this task A, I'm going to allocate it to thread B, and then this is going to take care of this particular task. Now, if this particular task creates subtasks, like I don't want to be bothered by it, let's have this thread handle it. So what this does is as this creates subtasks, it's going to get added to this internal queue that each thread has. Okay, each thread has its own queue, and then that gets queued up as the subtasks are created. Okay, so let's say you have main tasks. To break it down into two tasks, well, you're going to basically have two tasks over here, and then each one of them gets allocated to two threads, and then that breaks it down further as well. Now, you might be thinking, well, this is no different from just breaking it down at the top level, right? Well, the difference here is the concept of work stealing, which has been implemented. I told you one of the disadvantages of breaking it down at a very high level is that one of those chunks might not result in any work at all. Okay, you might have a huge array, you break it down into two, and then one part may be just smaller numbers which get processed really quickly, and another part may be really large numbers which takes a lot of time to process. Okay, so doesn't this have the same problem? You have one task going over here, all easy tasks, another chunk going over here, which is all the difficult tasks. Well, the way Java solves this problem is by using something called work stealing. The idea is it notices what load all these threads are doing. Okay, so you have all these chunks, and each thread is processing all the subtasks associated with those chunks. Now, if it notices one task has, it's getting freed up very quickly, right? Not a lot of work. Another task is really struggling. What it does is it takes tasks from the end of this queue where that's really struggling and assigns it to the task that's the thread that's getting relatively free. Okay, so it's taking care of distributing the work. It doesn't necessarily distribute it evenly, but what it does is when it realizes that one thread is it's getting done very quickly, it steals the work from another thread, and this concept is called work stealing. The way work stealing works is it looks at each of these queues. These queues happen to be D queues, by the way. D queue stands for double-ended queue. So you can remove things from the front as well as from the back. So when it steals work from another queue, it removes from the end so that this thing, whatever is picking up from on this side, is not going to be it's not going to be surprised like, where did my stuff go? And there are no concurrency issues. Okay, so that's how the work here ends up getting distributed eventually, and this is how the fork join pool works. So this is an architecture that is built in order to handle these kind of recursive breakdown of work into really small tasks. And this is the way for these thread pools to manage like loads and loads of tasks, small tasks, and not have a new thread be spawned for each and every task. Okay, so this is the fork join pool. So again, the steps to create the fork join pool and leverage it for solving this kind of a problem. First, you create a fork join task. Okay, so this is the Java doc for the fork join task. And this is an abstract base class for creating tasks that run with a fork join pool. Again, a fork join pool is our custom implementation. We're going to look at what you can do with a fork join task and how you need to code it. But usually, you don't directly use a fork join task. Okay, there are two sub implementations of the fork join task, and you get to pick from one of those. Okay, the two implementations are one's something called recursive action, and one other is something called recursive task. Okay, so these are the two use cases that I talked about earlier. And we say, okay, there might be recursive breakdown of work, which may not really need to be accumulated, versus recursive breakdown of work, which needs to be accumulated. Adding one to every element of an array is a good use case of where you can break down the work recursively, and you don't need to accumulate it back. All you need to do is just add one to that element and you're done, right? No accumulation needed. So that's one aspect. So that is recursive action. That's when you would use recursive action. The second is when you have something which is result bearing, like adding all the numbers of an array. Okay, in that case, what you need to do is you break it down and add like smaller chunks. But then what you need to do when you get those smaller chunks computed, you need to add them, and then you need to add those chunks and then the parent chunks and so on until you have one value, which is the total sum of all the elements in the array, right? For that, when you have a task that is result bearing, you use recursive task. When you have a task that is resultless, you use recursive action, right? So these are two implementation of a fork join task, which you need to create. You need to extend these classes and create what you want each recursive step to do, right? You need to write code there. Once you have a class like that, you create an instance of that and submit it to the fork join pool. And the fork join pool is going to say, okay, I got it. I'm going to take care of distributing this and recursively allocating, creating these tasks and then allocating threads for it. And I'm also going to make sure that not a single thread is going to get bogged down while the other threads are free. I'm going to do work stealing to make sure that if some thread is taking a lot of tasks and taking a lot of time, it is going to take that task and allocate it to another thread which is relatively free, and it's going to take care of all of that. All right. So in the next tutorial, I'm going to explain to you how this works by actually showing you a code demo. And if you have any confusion, it'll make a lot of sense then.